the antiprotons from the antiproton decelerator, that's the machine that we need here at CERN, come down this pipe right here. And they come into our apparatus, which is inside this large magnet. This is a very strong magnetic field to help to confine the charged particles that make antihydrogen. We mix the antiprotons with positrons inside this magnet trap, and that's where we capture them. That's where we have the very strong magnetic fields to capture the anti-atoms and hold on to them. So what we do is hold on to them for 1,000 seconds and then release them to make sure they were there. That's how you do this measurement. First, we improved how many antihydrogen atoms we can trap every time. We worked very hard to optimize this number, and we'll continue to work on that. That's something we really need to keep improving. The other thing is that we just waited. There wasn't a lot of extra work to do. We just had to be patient, wait for them, and release them to see how long they last. In other words, the device was capable of this from the beginning. All we did was investigate its potential at this point. On the atomic life scale, 1,000 seconds is forever. Things on the atomic life scale are measured in nanoseconds or smaller perhaps. So this is forever for an atom to be trapped. And the other important point is that since antihydrogen atoms are rare, they're difficult to make, they're difficult to trap. If you want to study them, you have two things that are to be considered. One is how many, and the other is how long you can talk to them. How long can you do an experiment on an antihydrogen atom? If you have fewer of them, but can talk to them for a long time, then you can do the same experiment that might take a lot of atoms in a short time. All right, so there's a trade-off. If you don't have very many but can interact with them for a long time, then you still have a good experiment. And that's why we're very excited. We think we're ready now to try to make the first measurements with these trapped anti-atoms. So we use the annihilation of the antimatter to see that it was trapped. The next step, and that's what we're reporting now, is to hold on to it. See how long can we keep it around so that we can study it. After all, that's what we want to do. We want to study the antimatter, compare it to matter, and see if they're the same. And by study, we mean interact with lasers or with microwave radiation to see what their structure is inside. How do they behave? Do they behave exactly like hydrogen?
Illustrated is the center of the alpha apparatus with the annihilation detector on the outside. Peeling away like an onion, we next see the coil windings for creating the magnetic minimum. The arrows illustrate the direction of the currents used to make the magnetic fields. Going further inwards, we find the electrodes. The electrodes are used to generate the electric potential which confines the antiprotons and positrons before they form antihydrogen. We now bring the positrons and antiprotons into contact. A positron is bound to an antiproton through a collision with a second positron. This forms antihydrogen. Here you see the magnetic minimum, shown as a bathtub. The antihydrogen is trapped like a marble rolling around in the bathtub. To detect the antihydrogen, We turn off the magnetic fields and the antihydrogen escapes. The antihydrogen then annihilates on the matter in the wall of the system. We track the annihilation products to determine where the antihydrogen annihilates.